Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. My name is Dafa Bayu Putranto, and in this afternoon, I will present to you a project which is titled Analog Electronic Instrumentation, in which my lecturer, my doctor is Dr. Suyanto, and my name is Dafa Bayu Putranto with the NRP of 0231 18400 So in this presentation, I would like to present to you a few contents. Here is the table of content of the presentation. Firstly, I will introduce, then I will provide the explanation, and then we will summarize. And lastly, we will show the references that we used to build this presentation. So firstly, let's jump into the introduction. So the background. Firstly, what is instrumentation? Instrumentation is the art and science of applying measuring instruments to objects. It aims to determine the value of a process variable to control the process variable so that it is close to the desired value or set point, as we call it. Instrumentation is implemented in measurement systems, monitoring systems, safety systems, and control systems. So instrumentation itself is applied in various industries such as the automation industry and process industry, which applications we will go into a little further down the slides. So the 4 to 20 milliamp standard signal is set as the international standard signal by the International Society of Automation, or ISA S20, which applies across various industries. Therefore, it is important to dive into its fundamentals and also its applications. So here's a quick review of the process variables. Firstly, we have flow, level, pressure, temperature, and process analyzer or analytes. So for example, that is pH or composition. So this arrangement of process variables, we have arranged it such that from the fastest response time to the slowest. Flow has the highest or the fastest response time, and process analyzer has the slowest response time in light of the measurement. So for example, if you measure flow, we can get the result way faster than when we measure process analyzer such as pH. So here are some of the measurement instruments, example of them. Firstly, we have electromagnetic flow meter, which measures flow. And then for level, we have magnetic level gauge or MLG. And for temperature, we have thermometer. We have pressure gauge for pressure. Then we have pH analyzer for pH, obviously. And it's also arranged according to the process variables in which the instrument measures. So next, we have the problems. Problems of concern within this presentation comprise firstly, what is the 4 to 20 milliamp signal? And secondly, how is it implemented in the process industry? And then third, what are the components of the 4 to 20 milliamp current loop? And lastly, what is an example of an application of the 4 to 20 milliamp current loop? So this presentation aims, the aims concerned within this presentation comprise, firstly, to explain the fundamentals of 4 to 20 milliamp standard signal. Secondly, to explain its implementation in the process industry. Third is to mention and explain the components involved with 4 to 20 milliamp current loop. Lastly is to explain or to go over its applications. So the contributions of this presentation is first to provide an understanding of the concept of 4 to 20 milliamp standard signal from its fundamental concepts to its application by presenting and summarizing in a straightforward and practical manner. So let's jump into the explanation. So the standard instrument analog signals. So we are talking about analog signals here, which has a range between 4 milliamps up to 20 milliamps, 0% to 100%. So we have 4 milliamps that represents 0% of the scale and 20 milliamps that represents 100% of the scale. So this could represent any process variable that is measured by the sensor, and then the signal, which is the output by the sensor or the transmitter, will be represented in current range between 4 to 20 milliamp range. That means 0% of the scale or 100% of the scale. So in between those ranges, we have this table, the practical table, which you can just see the linear regression from 4 milliamps to 20 milliamps. So that's 0% for 4 milliamps, 25% for 8 milliamps, and so on until 100% for 20 milliamps. So the scale is also referred to as a live zero standard because their values do not touch zero. So the lowest value is 4 milliamps. This is to differentiate between a legitimate 0% value and a failed signal. So for example, if we have a failed signal or a broken wire, it will show 0, but if we have a 0 signal, it will show 4 milliamps. So the operators or the engineers can actually detect and differentiate between what is a failure in the instrument and what is an actual legitimate 0% signal. So here's a little note. All analog instruments sending and receiving signals must be compatible. So we will see that in the next slide. So here's an example of a configuration of the instruments involved, involving the 4.4 to 20 milliamp signals. So this is a temperature measurement system. And here we have the thermocouple as a sensor. So it has an iron and a constantan, which inputs the range between 50 to 250 degrees Celsius. So it measures the temperatures between that range, and it outputs in millivolts in voltage. It outputs voltage in a range of 2.585 to 13.555 millivolts. So the sensor or the thermocouple is connected to the temperature transmitter, or usually symbolized as TT in the PNID. So here's the diagram, which inputs between 2.585 to 13.555 millivolts and outputs a range of 4 to 20 milliamps. So if you see right here, we need to take note of the fact that the output range of the previous instrument has to be compatible with the next instrument that it is connected to. So the output range of the thermocouple is the same as the input range of the temperature transmitter. So that way we don't lose any information, whether we have the value that is not compatible in between those ranges. So here we have a compatible one, and if you follow the wire, it goes into here we have a power supply and a resistor. A resistor of 250 ohms, which in here it inputs a range between 4 to 20 milliamps from the temperature transmitter, and it outputs the range of between 1 to 5 volts. So if we remember basic physics, in which the first law of Ohm is that we have V equals to I times R, or voltage equals to current times resistance. So if we have a current of 4 milliamps, we multiply that by 250 ohms, we have 1 volt. And if we have a current of 20 milliamps, we multiply that by 250 ohms, we have 5 volts. So that's how we get 1 to 5 volt input. So the resistance in here, the wire is then connected to a temperature indicator, which then shows the information of the temperature measured by the thermocouple. So the input range of the temperature indicator is between 1 to 5 volts, and its output is between the 50 to 250 degrees Celsius, same exact temperature that is measured by the thermocouple. So all of this information is mentioned in the data sheet of each of the components. So we have the thermocouple, the temperature transmitter, and the temperature indicator. So here, to summarize, in the table below is just another table that shows the input range and output range, in which you can see that the output range of the previous instrument is compatible with the input range of the next instrument. So let's just move on to the industrial case. We have the final control element correlation, in which we have the process that is connected to the measuring device. A measuring device is connected to the process. So this measuring device senses the process variable, or PV, which is expressed in a between 4 to 20 milliamp signal, which is then fed into the controller, which decides accordingly to the logic that is programmed by the operator or the engineer. So the controller then outputs MV, which stands for manipulated variable, also expressed as a 4 to 20 milliamp signal, which influences the final control device or final control element. So the final control element could be a control valve or maybe a variable speed device, VSD. So it depends on the process itself or on what you want to do with the. So final control elements often have adjustable ranges to achieve an accurate correspondence between the analog signal and the desired control action. So in here we have a little note in which PV and MV current signals are not always equal, i.e. controller may be reverse acting or in manual mode. So that's the case for the industrial case. So we move on to the standard instrument analog signals, in which first we have a graph of current with respect to signal in percentage, current in milliamps. So here's the relation between the 4 to 20 milliamp standard signal, which is usually linear to the instrument variable. So therefore, it can be expressed as the linear equation, basic linear equation, which is y equals to mx plus b, or y equals to mx plus c if you wish, where y is the output of the instrument and x is the input of the instrument, m is the slope or the gradient, and b is the y-interception or live zero. So here's the graphic. As you can see, the b is at y equals to 4, because we have a signal of between 4 to 20 milliamps. So 4 milliamps is the live zero. And here we can substitute calculate the gradient m by dividing 20 minus 4 divided by with 100% minus 0%. So as you know, the formula for gradient is the displacement of the vertical displacement divided by the horizontal displacement of the graph, the linear graph. So in its real application, i.e. in a PLC, the slope m is referred to as rate, and the y-interception b is called offset. So b is also called offset, and m is also called rate in the setting of a PLC, or programmable logic controller. So here's a calculation example in which we use a control valve as the instrument of interest. So the controller outputs a signal of 8.55 milliamps to a direct responding control valve, where 4 milliamps is fully shut and 20 milliamps is fully open. So the question is, how far is the control valve at this manipulated variable signal level? How far open is the control valve? So we have a signal of 8.55 in a range of 4 milliamps to 20 milliamps. So here we just substitute the 8.55 into the equation, in which 8.55 substitutes to y because it is the controller output. So 8.55 equals to 16 over 100 x plus 4. And the question is, how far open is the control valve at this manipulated signal level? So it is asking for x. So x, we just move it to the left, move sides, and then we obtain x value valued at 28.4%. So in here, the control valve will open at 28.4% of its opening when it receives a signal of 8.55 milliamps from the controller. So right there, here's the diagram. And note that the range values, i.e. 100 minus 0 depends on the final control element. In this case, the valve opening is expressed in 0 to 100% range. Also, a reverse acting instrument gives a negative slope in the linear equation. So here we assume that we know that the instrument has a direct responding control valve. So the gradient is positive, the gradient is up. So it is all, the graph is as we've seen in the previous slide. But if the instrument is reverse acting, the correlation between the output and the input of the instrument is reversed. So it is an inverse function in which it is a minus in the slope. So the slope is negative. So the bigger the input, the smaller the output. But in this case, the bigger the input, the bigger the output. So here's another one. Continuing from the previous example, electronic temperature transmitter is ranged 50 to 140 degrees Fahrenheit, and with an output with a 4 to 20 milliamp output signal. Calculate the current output if the measured temperature is 79.79 degrees Fahrenheit. So here we can use a per unit calculation in which the per unit ratio is calculated by subtracting 79 with 50 and then dividing it with 140 minus 50. So as you know, we have the signal measured temperature is 79. So 79 minus the bottom lower value, which is 50, divided by the whole range. So the whole range is 140 minus 50. So here we obtain a value of 32.22%, which is the x. So that is the x. We just substitute it to the previous equation, which we've seen before. Y equals to 16 over 100 times 32.22 plus 4. So the result Y is equals to 9.16 milliamps. So that's the value of the current output when a measured temperature is 79 degrees Fahrenheit. So the same note applies that the range of values, i.e. 100 to 0, depends on the final control element. In this case, the temperature transmitter has same range under there. So we have a number line calculation tool. So this is just to explain a quick and a practical tool which engineers and operators use to explain between ranges and values. So here, for example, if we have a length, which we have a value at 14.4 milliamps. So in the range, this is the whole range from 4 milliamps to 20 milliamps, which represents 0% to 100%. If we have a value of 14.4 milliamps, the length is the value that we have minus the 0% value, which is 4 milliamps. So we have 14.4 milliamps minus 4 milliamps. That means we have a length of 10.4 milliamps. So the whole from 4 milliamps to 20 milliamps is called the span. Span is 16 milliamps because we obtained that from 20 minus 4 milliamps. So we have 16 milliamp span. So the percentage, we obtain that by using the simple mathematical calculation. So we divide the length by the span and multiply that by 100, which we obtain a value of 65%. So 14.4 milliamps equals to a 65% value in the percentage domain. So this is used to convert, it can also be used to convert between scales. For example, a transmitter example we have here, we have a span of 30 psi, in which we have a span which corresponds to a 40 milliamps span. So 40 milliamps means from 10 milliamps to 50 milliamps, and 30 psi we obtained that from minus 5 psi up to plus 25 psi. So here, if we have a value of plus 25 psi, we have a length of plus 25 minus 5, which is 17. So from minus 5 to 12, that's 17 in length. The question is, what is the length in milliamps? So it has a linear proportional correlation. So we can just use the equation on the right. So here we just calculate 17 over 30 equals to x over 40. in which we obtain X as 22.67 milliamps, so that we conclude that a positive 12 psi pressure applied to the transmitter corresponds to a 22.67 milliamps plus 10 milliamps equals to 32.67 milliamps. So we add 10 because the live zero value is 10, so we have to be careful. We not forget to add 10. So then we have a per unit calculation continued. So this is an example of the level transmitter example, in which first we have an input range between 15 to 85 inches of liquid level. We have the same graph, but we have to take note of the range or the values of the live zero or the y-interception and the rise and the run. So the rise is the vertical displacement and the run is the horizontal displacement. So the x-axis represents the percentage from 0% to 100%, and the y-axis represents the level in inches. So here we have a lower value, and here we have an upper range value, URV, and our LRV is lower range value. So that is represented in inches. We have a URV of 85, we have a LRV of 15. So then we can just obtain the linear equation, which we go by y equals to mx plus c, or y equals to 85 minus 15 times x plus 15. So we have y equals to 70x plus 15. So, or in other words, we can just put it as input equals to URV minus LRV per unit times per unit value plus LRV. So the output is also calculated in a similar manner. So the range is between 4 to 20 milliamps. And here we have the y-axis as current between 4 to 20 milliamps. And we have the x-axis still as the percentage from 0 to 100%. So then we just calculate the equation, which is y equals to 16x plus 4. And the output also can be expressed in as URV output minus LRV output multiplied by the per unit value plus LRV output. So then this is the per unit calculation, in which we have seen an example of that before, but here's just to go into a little more detail. So therefore, the per unit value may serve as the link between the input and output as such. So here, if we have an input, this is a block diagram, simple block diagram. We have an input that goes into the instrument, in which the input has a range between the LRV input and the URV input, or the lower and upper range values of the input. And the instrument then outputs an output between the LRV output and the upper range output, value output. So here we have the mathematical correlation between the input and outputs. We have input minus LRV input over URV input minus LRV output. So that's just the same calculation as we had before. And that equals to the per unit of span from 0 to 1 inclusive. That is also equal to the output minus LRV output over URV output minus LRV output. So here's the example. We have a level of 32 inches. What is the milliamp value? So the first step is to take is to convert inches into per unit ratio, and then to convert per unit ratio into milliamp value. So step 1, let's do it. So 32 equals to 70x plus 15, and in which we have x equals to 0.2429 or 24.29%. And then step 2, we just substitute the 24.29% into the linear equation that we have of the output, in which the output is presumed as between 4 to 20 milliamps range, in which from that we have the linear equation as such. So we just substitute the x into the x, and we obtain a milliamp value of y equals to 7.886 milliamps. So there you go. A level of 32 inches corresponds to a milliamp value of 7.886 milliamps. So here's a little bit of additional knowledge, in which I reference the fundamentals of 4 to 20 milliamp current loops. So what is the 4 to 20 milliamp current loop? we have a current loop which comprises of its components, in which the current flows through all of the involved components. In this picture, we have voltage, total voltage, or usually it's a power supply, and we have the resistances, that is shown as R1, R2, and R3, which these can be transmitters, PLCs, or anything else that causes a voltage drop. And then we have one current that flows throughout the loop. So the current loop refers to the current that flows through the loop. So the current I, according to Ohm's law, is the same everywhere in any component of the loop, simple loop. So here's the analogy. We have a tank right here. The tank is represents the power supply, and the water wheel represents the resistors, in which anything that causes a voltage drop. The water pipe represents the wires, and the tap represents the controllers. I mean the actuators. So there you go. A little bit of history behind the 4 to 20 milliamp signal. So the 0 milliamp signal is hard to model. And when we pass through the values between like small values like 0.5 milliamps, 1 milliamps, etc., it's very hard to sense. And then technically we can distinguish a true zero signal value from a system or component failure. So that's just like what I said in the beginning. Distinguish a true zero or a legitimate 0% value or from component failure, for example, a broken wire. So here's an example of the current loop that we have usually in the industry. So a few components, we have sensors, transmitter, a power supply, and then a process controller. So the sensor provides an output value representative of the parameter being measured. So for example, the example we had before was a thermocouple. And then we have the transmitter. The transmitter conditions the output and converts it into a proportional current between 4 to 20 milliamps. So that will be the temperature transmitter if we had referred to the previous examples. And then we have the power supply right here. And then we have a receiver that converts the current to a voltage for use in a display. So the receiver usually corresponds to a process controller or anything else. It can be an input to a PLC or as such. So let's go over the components one by one. First, we have sensors. So its job is to measure the process parameter, and it generally outputs a voltage, and its signal sometimes is unusual to complexity, and also it is subject to noise. So here are some of the issues of sensors. Sometimes the output signal could be interfered with noise. It could be electrical noise or any other, maybe temperature or any other external objects or variables that can interfere with the measurement. So next is how far can it run before the wire becomes the problem, because a wire has a resistance in itself. So a longer distance of wire, or we have to have the proper material and the proper sizing of the wire and proper configuration of the system so it can run smoothly. So lastly, is it a useful signal? Because sometimes it's so small. This is referring to the signal that is obtained as the output of the sensor. Okay. So the second component we have is the transmitter, which takes the signal that measures the process variable and regulates the 4 to 20 milliamp signal. So as we mentioned before, the 4 milliamp represents the 0% of the scale and 20 milliamp represents the 100% of the scale. So sometimes we also have the range in PSI or in pressure. We have 3 PSI or pounds per square inch, which represents the 0% of the scale, and 15 PSI, which represents the 100% of the scale. So this is a picture of an example of a temperature transmitter. So the next component is a power supply. So the power supply, some of the rules to use when implementing a power supply is, firstly, we have to have voltage level, which must be higher than some of the maximum required for transmitters. We have the max, it must be also be higher than the IR or voltage drop in all receivers and the voltage drop in wires. So the power supply has to have a voltage value above all of these summed. So usually it comes in a 12-volt DC or 15-volt DC or 24-volt DC or 36. Usually the most common is the 24-volt DC power supply. So here's an electrical diagram of it, in which it is represented by the plus and minus, which represents the positive and negative poles of the power supply. So the next component, we have the receiver. So the receiver receives the current signal, the 4 to 20 milliamp current signal, and then it converts it into the voltage values, which is the input of the display or the indicators, as we generally speak. So for example, we have panel meters, the chart recorders, or PLC inputs, etc. So what the receiver has is an internal sense resistor to calculate the voltage drop across, which calculates the current, then scales it. So it has a little internal sense resistor, which converts it and calculates the voltage drop, then calculates the current, and then it scales it to the needs of the indicator. So this can provide additional outputs also, such as relays for alarms, and also sometimes has built-in power supply. So sometimes we don't even need a power supply, as it is built into the receiver. There is an example of a picture of a receiver. And then the next component is wire. So the wire adds an extremely small amount of resistance in the current loop. And because the current is the same in the loop, therefore there is no added inaccuracy. So this is one of the advantages of the current loop, because the current is the same in all of the loop. So there is no added inaccuracy in terms of the measurement, in terms of the data or the information being sent over those wires. So here is a table that shows a chart of wire resistance in terms of the diameter, also the length. So the longer and the bigger the wire, the greater the resistance that it can provide, that can also affect the loop. So to summarize the presentation, first, that the 4 to 20 milliamp current range serves as the standard signal that is set by the International Society of Automation, or ISA, organization that applies across various industries, including the process industry. And then secondly, its implementation in the industry involves various components that serve its purpose in its system, such as the measurement system and the control system. So the 4 to 20 milliamp current loop comprises sensors, transmitters, power supplies, receivers, and wires. Last but not least, examples of the application of the 4 to 20 milliamp standard signal and its calculation was provided for instruments such as control valve, temperature transmitter, and also the level transmitter. So a little bit more about the pros and cons of the current loop for between 4 to 20 milliamp current loop. So the pros is because it's simple to configure, and then it uses less wire and connections. Also, it can reach longer distances, which will be tolerable, as opposed to voltage output signals, because the voltage has a major drop but as opposed to the current being the same in all of the loop. And then we have a low sensitivity to electrical noise. And then lastly, we have the easily detected signal or power loss. So the cons of using a 4 to 20 milliamp current loop is that it only has one parameter transmission. So 4 to 20 milliamp range transmits only one information. So it can only, for example, if we measure temperature, then the value of the transmission or the current that is provided only represents the temperature in which we're trying to measure. It doesn't represent anything else. So only one parameter transmitted. Next, it is susceptible to ground loops. And lastly, it has isolation requirements. So here's a few references that we used. First, we have Bolton, and then Fogg, lessons in Bolton instrumentation and control systems. We have about lessons in industrial instrumentation, introduction to industrial instrumentation. We have Moto Gray, piping and instrumentation diagram development. And then last but not least, we have ISA standard, American Standards Institute, ISA, the Instrumentation Systems and Automation Society, ISA S 5.1. So that is it for my presentation. Thank you for your attention. I apologize if there's imperfections, but thank you. Assalamualaikum warahmatullahi wabarakatuh.